Good morning students. Welcome to 11th standard chemistry video class. We are discussing lesson 12 basic concepts of organic reactions. In our last video class we completed up to nucleophiles and electrophiles. In this video we have to start with the next topic, electron displacement effects in covalent bonds. Electron displacement effects in covalent bonds. Some of the properties of organic molecules such as stability, reactivity, basicity, etc. are affected by the displacement of electrons that takes place in its covalent bonds. Here, the movement of electrons in the covalent bond of organic compounds will affect the properties such as stability, reactivity, basicity, etc. This movement can be influenced by either the atoms or groups present in close proximity to the bond or when a reagent approaches a molecule. Here, the movement of electron in covalent bond is due to the atom or group present in molecule or any other reagent approaches the molecule. These displacement effects can either be permanent or temporary. In certain cases, electron displacement is due to the atom or a substituent group present in a molecule which makes a permanent polarization of the bond, and it leads to the fission of the bonds under suitable conditions. Here, the electron displacements are categorized into inductive effect, resonance effect, electromeric effect, and hyperconjugation. Here, inductive effect is denoted by I. Resonance effect is denoted by R. Electromeric effect is denoted by E. Let me discuss one by one. First, we will discuss inductive effect. Inductive effect. Inductive effect is denoted by I. Here, we are having the definition for inductive effect. Inductive effect is defined as the change in the polarization of a covalent bond due to the presence of adjacent bonds, atoms, or groups in a molecule. The inductive effect is a permanent effect. Here, due to the presence of adjacent bonds, atoms, or groups in a molecule, there should be change in polarization of a covalent bond. It is said to be inductive effect. This inductive effect is explained by taking two examples, namely ethane and ethyl chloride. In ethane, carbon bond carbon is nonpolar, where in ethyl chloride, carbon bond carbon is polar. It is explained here. In ethyl chloride, already we know that chlorine is more electronegative than carbon. Hence, chlorine attracts the shared pair of electron between carbon bond chlorine in ethyl chloride towards itself. Due to this reason, there should be slight negative charge is developed on chlorine and slight positive charge is developed on carbon to which chlorine is attached. To compensate it, carbon 1, that is C1, draws the shared pair of electron between itself and carbon 2, that is C2. This polarization effect is said to be inductive effect. The magnitude of the charge separation decreases rapidly as we move from carbon 1. Here, inductive effect does not transfer electrons from one atom to another atom. But the displacement effect is permanent. Based upon the ability of atom or group, that is withdraw electron density or release electron density, the inductive effect is classified as plus I groups and minus I groups. Here, their ability to release or withdraw the electron through sigma covalent bond is called plus I effect and minus I effect respectively. Here, electron withdrawing groups are minus I groups. The electron donating groups are plus I groups. What are minus I groups? Highly electronegative atom and group with an atom which carrying a positive charge or electron withdrawing groups are minus I groups. Here we are having some examples for minus I groups. Fluorine F, chlorine Cl, carboxylic acid COOH, nitro group NO2 and amine group NH2 are the examples for minus I groups. If the electronegativity value of substituents are higher, then greater will be the minus I effect. The order of the minus I effect of some groups are given here. Next one, what are plus I groups? Highly electropositive atoms and groups which carry a negative charge or electron donating group are plus I groups. Here we are having some examples for plus I groups. Alkali metals, alkyl groups such as methyl, ethyl, negatively charged groups such as CH3O-, C2H5O- and COO- are examples for plus I group. Lesser the electronegativity value, greater will be the plus I effect. The relative order of plus I effect of some alkyl groups are given here. Next, let me discuss the influence of inductive effect on some properties of organic compounds. We have to discuss two concepts, namely reactivity and acidity of carboxylic acids. First, we will discuss reactivity. When a highly electronegative atom such as halogen is attached to a carbon, then it makes carbon bond halogen polar. That is, it creates a charge. A partial negative charge on halogen and partial positive charge on carbon. Due to the presence of minus I group, it makes the attack of negatively charged nucleophile towards the polarized carbon atom, and hence it increases the reactivity. It is explained with an example. In this tertiary butyl bromide, bromine is minus I group. It is attached to the carbon. Hence, the bond between carbon and bromine is polar. Hence, partial negative charge is created in bromine and partial positive charge is created in carbon. Therefore, nucleophile with negative charge may attack the polarized carbon and reactivity is increased. Next, if a minus I group is attached nearer to a carbonyl carbon, it decreases the availability of electron density on the carbonyl carbon and hence increases the rate of the nucleophilic addition reaction. Next, we will discuss acidity of carboxylic acids. When halogen atom is attached to a carbon which is nearer to a carboxylic acid group, this halogen withdraws the bonded electron towards itself and makes the ionization of H plus easy. Hence, the strength of an acid increases. If more number of halogens, that is electron withdrawing group, are attached, then greater will be the acid strength. It is explained by taking some examples. Monochloroacidic acid, dichloroacidic acid, trichloroacidic acid. Here we are having the order of acid strength for above compounds. Acid strength of trichloroacidic acid is greater than dichloroacidic acid, which is greater than chloroacidic acid, which is greater than acetic acid. Similarly, acidity in the carboxylic acids is due to the plus I effect of alkyl group. Here, alkyl group are electron donating group. If more number of alkyl group is substituted, there should be decrease in acid strength. The order is given here. Hence, we completed inductive effect. Next topic, electromeric effect. Electromeric effect is represented by E. It is an temporary effect. Electromeric effect operates in unsaturated compounds, namely alkene and carbonyl compounds, in the presence of an attacking reagent. Let us consider two different compounds. First one, compounds containing carbonyl group. Second one, unsaturated compounds such as alkenes. Consider the first compound, that is carbonyl compound. When a nucleophile approaches the carbonyl compound, the pi electrons between carbon and oxygen is instantaneously shifted to the more electronegative oxygen. This makes the carbon electron deficient and thus facilitating the formation of a new bond between the incoming nucleophile and the carbonyl carbon atom. It is shown here. Consider the second compound, that is alkene compound. When an electrophile such as H+ approaches an alkene molecule, the pi electrons are instantaneously shifted to the electrophile and a new bond is formed between carbon and hydrogen. This makes the other carbon as electron deficient and hence it acquires a positive charge. It is shown here. Like inductive effect, the electromeric effect is also classified as plus C effect and minus C effect based on the direction in which the pair of electron is transferred to form a new bond with the attacking agent. In this example, when an pi electron is transferred towards the attacking reagent, it is called plus C effect, that is positive electromeric effect. The addition of H+ to alkene is an example for plus C effect. In this example, when the pi electron is transferred away from the attacking reagent, it is called minus C effect or negative electromeric effect. The attack of Cn- on a carbonyl carbon is an example for minus C effect. Hence, we completed the topic electromeric effect. Next topic, resonance or mesomeric effect. The resonance is a chemical phenomenon which is observed in certain organic compounds possessing double bonds at a suitable position. Hence, resonance takes place in organic compounds containing double bonds. Certain organic compounds can be represented by more than one structure and they differ only in the position of bonding electron and lone pair of electrons. Hence, this structure are called resonance structure or canonical structure, and this phenomenon is said to be resonance. It is also called as mesomerism or mesomeric effect. It is explained with an example. The structure of benzene and 1,3-butadiene cannot be represented by a single structure. Hence, they contain double bonds. Therefore, they should be explained on the basis of resonance hybrid. Consider 1,3-butadiene. It is expected that the bond between C1-C2 and C3-C4 should be shorter than that of C2-C3. Since C1-C2 and C3-C4 contains double bond, where C2-C3 contains single bond. But the observed bond lengths are of same. This property cannot be explained by a simple structure in which two pi bonds localized between C1-C2 and C3-C4. Delocalization of pi electrons is shown here. These resonating structures are called canonical forms, and the actual structure lies between these three resonating structures and is called resonance hybrid. The resonance hybrid is represented here. Like inductive effect and electromeric effect, mesomeric effect is classified as positive mesomeric effect and negative mesomeric effect. Positive mesomeric effect is denoted by plus M or plus R, where negative mesomeric effect is denoted by minus M or minus R based on the nature of the functional group present adjacent to the multiple bond. First, we will discuss positive mesomeric effect. This effect occurs when the electrons move away from the substituent attached to the conjugated system. It may occur when the electron releasing substituents are attached to the conjugated system, that is, compounds containing double bonds. The electron releasing groups are usually denoted as plus R or plus M groups. The example for plus M effect is given here. Next one, negative mesomeric effect. This effect occurs when the electrons move towards the substituent attached to the conjugated system, that is, compounds containing double bond. It may occur if the electron withdrawing substituents are attached to the conjugated system. These electron withdrawing groups are usually denoted as minus R or minus M groups. The examples for minus M effect is given here. Hence, the properties such as acidity of phenol is explained by resonance phenomenon. The phenoxide ion is more stabilized than phenol by plus M effect, and hence resonance favors. Ionization of phenol to form H plus and shows acidity. It is shown here. Hence, we completed the topic resonance or mesomeric effect. Next topic, hyperconjugation. Hyperconjugation is due to delocalization of electron of sigma bond. It is due to interaction of electrons of a sigma bond, usually in carbon-hydrogen bond or carbon-carbon bond with the adjacent empty non-bonding p orbital or an antibonding sigma star or pi star orbitals, resulting in an extended molecular orbital. Hyperconjugation is a permanent effect. Hence, it needs alpha CH group or a lone pair on atom like nitrogen, oxygen adjacent to a pi bond, where carbon contains sp2 hybridization. Since nitrogen contain one lone pair electron, where oxygen contain two lone pair electrons. Hence, the hyperconjugation occurs by overlapping of the sigma bonding orbital or orbital containing a lone pair with adjacent pi orbital. It is explained by taking three examples. Consider example 1. In propene, the sigma electrons of CH bond of methyl group can be delocalized into the pi orbital of doubly bonded carbon, which is shown here. In this structure, the sigma bond is involved in resonance and breaks in order to supply electrons for delocalization, giving rise to three canonical forms. Consider structure 2, structure 3 and structure 4. There is no bond between an alpha carbon and one of the hydrogen atoms. Here, hyperconjugation is also known as no bond resonance or otherwise called Baker-Northern effect. Here, structure 2, structure 3, structure 4 are polar in nature, since it contains charge. Consider example 2. Hyperconjugation effect is also observed when atoms or groups having lone pair of electrons are attached by a single bond and in conjugation with a pi bond. Here, more than one structure is obtained. It is shown here. Consider example 3. When electronegative atoms or group of atoms are in conjugation with a pi bond, they pull pi electrons from the multiple bond. In case of carbocation, greater the number of alkyl group attached to the carbon bearing positive charge, greater will be the hyperconjugate structure. Here, tertiary carbocation is greater than secondary carbocation greater than primary carbocation. Hence, we completed the topic hyperconjugation, and also we completed electron displacement effects in covalent bonds. Hence, we completed lesson 12 basic concepts of organic reactions. Thank you.